Hi, welcome to Concept-Based. I'm John Hepworth. This one's for Year 11 Advanced students, and we're beginning a new topic. We're beginning the trigonometric topic. Now, the trigonometric topic is broken up into a few parts in the scope and sequence that's recommended by NESA. And so there's actually two sections, well, three. There's week 10 at the end of this semester, end of this term, sorry, then weeks 1 and 2, and then weeks 3 to 5. With some different sections. So the measure of angles is at the start, and then the identities and equations are secondary. So I'll be covering all of those in this new grouping that I'll be creating for Year 11 Advanced in Trigonometry. So I want to make it very, very clear, first of all, that this comes from Year 10 trigonometry that we're building upon. As almost everything in the advanced course, we're building upon Year 10. In Year 10, you understood trigonometry as a practical application idea. You had problems you needed to solve where you had missing angles and missing lengths, and you went ahead and solved them. Trigonometry in the advanced course is very different to that. It is taught, it becomes far more like a function. And so we are going to do far more things with the idea of the function part of it, not just these sides and angles that you were finding in Year 10. However, the first concept that we're talking about today is the exact ratio triangles, so it is a bit of a practical one. But I want to say when I'm doing this that this is one way of thinking about trig in triangles as an angle with sides. There's another way you should be thinking about trig, which is in a unit circle, which we'll cover in the future. You should also be thinking about trig as what its graph looks like. Because if you can link all of these three things together, how the triangle looks, what the unit circle is doing, and what the graph is doing, at the same time in your mind, then trigonometry will become significantly easier for you. If you only ever think in terms of the Year 10 style of it's an angle, it's a length of a side, then you're just going to struggle to find these concepts sinking in as much as possible. But like I said, today's just on one part of these things. It's not the unit circle, it's not graphing, it's just the triangles. And the question here that we've got is find the exact values for sine theta, cos theta, and tan theta, where theta is a multiple of 30 degrees or 45 degrees. So what I'm going to do essentially is just look at the exact value triangles, and then I'm just going to pose a question and see what you think would be right, but not delve into the unit circle. So let's see how we go. Okay, so with these exact values, we create essentially exact value triangles. And there's two different triangles that we create to solve these exact values for us. Now, yes, they are on the formula sheet, so no, you don't have to remember them, but I highly recommend all of my students to be able to draw these, straight off the top of their head, because every time you have to go to the formula sheet to find something on the formula sheet, it's costing you time. And we want your time to be maximized doing difficult questions in the HSC. So try and commit these to memory. They're not hard to commit to memory. So I would recommend that you try and commit them to memory. Oh, my OneNote does not like the spelling of the sine, the cos, and the tan. Let's ignore that and get it looking a little less red underlines for sine theta, cos theta, and tan theta. Okay, so the first one, let's do the 45-degree triangle first. I think teachers are teaching kids isosceles triangles in Year 7 and 8 poorly. Because if I say to you, imagine an isosceles triangle, I guarantee that the isosceles triangle that you're imagining is this one. It's just the standard isosceles triangle, right? It's the standing upright with its two equal sides. And we know that these base angles are equal. I think we should actually be teaching kids isosceles triangles in the way that it helps us in Year 11 and Year 12 so that our fundamental understanding is improved. The isosceles triangle that helps you in trig is this one. It still has two equal sides. It still has two equal base angles, but it's on its side, and we're just not used to seeing it like that. But if you can remember that this is the way it looks, then you'll be able to fill in all the details, no problems. So these side lengths are actually not just the same, but this is a special isosceles triangle. It's a right angle isosceles triangle, which it has to be for us to do our trigonometric calculations. So our right angle isosceles triangle has 90 degrees missing from it. Base angles are equal, so each one is 45 degrees. So here we have 45 and 45. Now we say that the side lengths are unit 1 that are equal. Now, you know, with trigonometry, all of the trigonometric expressions are ratios. So it doesn't actually matter how big this triangle is. It could be 10 by 10 or 50 by 50. What we care about is the ratio of the sides. So 1 by 1 is the easiest. So then we do a little bit of Pythagoras in our right angle triangle. 1 squared plus 1 squared is 2. And we take the square root of 2 and find the long side. So we now have sine 45, cos 45, and tan 45 from this one triangle. So sine 45, pick whichever 45 you like. The opposite side is always 1 because they're the same lengths, and it's over root 2. Cos is the same because the adjacent and the hypotenuse sides are the same in this. And then tan's a little different. It's an opposite 1 over an adjacent 1, so 1 over 1 or 1. So tan 45 is 1. And hopefully you relate your tans angles to gradients as well. It's good to link those concepts together. So when you're thinking about tan, try and think of a gradient. Okay, so there it is. There's our 45-degree angle triangle. Easy to create. It's isosceles. It's on its side. But I think we should always think of isosceles triangles being like this. And then we can get these 45-degree angles. Okay, there's another one that we need to do as well. And that is an equilateral triangle. And the equilateral triangle is to give rise to the 30 and 60 degree angles. Now this equilateral triangle does give rise to 60 degree angles, but it doesn't give rise to a 30 degree angle. So to get that 30 degree angle, we're going to chop the triangle in half. And that gets us a 30 degree angle up in here. So I'm going to get rid of this part and go back to in half. Now, the side of the equilateral triangle when we had all sides equal is not length 1 because we chopped them in half. So we want to make it easy for ourselves. So we actually make the length of the equilateral triangle side 2 so that when we chop it in half, it equals 1. And then we just use Pythag to find the unknown side again. In this case, it's the short side, not the long side. So 2 squared is 4 minus 1 is 3 and we get root 3. So now we can actually get sine 30, cos 30, tan 30, and also sine 60, cos 60, and tan 60. So sine 30, opposite over hypotenuse, 1 over 2. Cos 30, adjacent over hypotenuse, root, I lost what I was looking at then, root 3 over 2. Tan 30, opposite over adjacent, 1 over root 3. Sine 60, opposite over hypotenuse, root 3 over 2. Cos 60, adjacent over hypotenuse, 1 over 2. And tan 60, opposite over adjacent, root 3 over 1, or just root 3. And so there we have it. The 30 degree angles, 45 degree angles, 60 degree angles, we can find them all from these exact value triangles. And like I said, they're in the formula sheet, but I would love it, if you can memorize them and just draw them super quickly, because once you've memorized them, like obviously I don't need to go through that process of that explanation. I can just draw my triangles immediately and get my 45 degree angle, which is so much faster than looking up the formula sheet. Now, I did say I'd extend this question a little bit because it does say here exact values where it's a multiple of 30 and 45. So it could go beyond 45. What about then if we had to do sine 90? What would that equal? And so what I try and take into consideration, again, the unit circle will help you with this, but what if my triangle that I was drawing, which used to have a 45 degree angle and had an opposite of 1 over root 2, actually got bigger and bigger. Now we've seen a 60 degree one, so then we could draw like that's a terrible line. We could draw a larger angle like this. And then it gets larger and larger, and this side keeps moving around to the top here until it gets to 90. And you'll notice that this side here is starting to become the same length as this side here. And so when it gets up to 90, it does get to the same length. And so you can actually get 90 equals, so the opposite 1 over the hypotenuse, the same length 1, sine 90 is equal to 1. Now you can go through this conceptual understanding and do 180s and the 270s, and we could even do the ones like 30 degree angles into those second, third, and fourth quadrants, but we'll leave that for the unit circle. What I'd love you to have at the end of this video is just an ability to draw those exact triangles and get the exact values out of them immediately.